Look up at the night sky on a clear evening, and you'll see countless pinpricks of light shimmering against the darkness. But what if I told you those tiny dots aren't just peaceful, distant suns? Some of them are cosmic monsters raging infernos of unimaginable power, capable of bending the very fabric of space and time. Stars like these don't just burn, they dominate. They rewrite the rules of physics, defy our understanding of energy, and sculpt entire galaxies with their sheer might. And today, we're about to meet the most extreme among them, the 30 most powerful stars in the universe. Imagine a stellar behemoth so colossal that if it replaced our Sun, its surface would stretch beyond the orbit of Jupiter. Picture a star so luminous that it outshines entire galaxies, or one so dense that a teaspoon of its material would weigh more than a mountain. These aren't just theoretical ideas, they're real cosmic titans, each with a story more astonishing than the last. Some explode in supernovae so violent they're visible across the cosmos, while others collapse into black holes, swallowing everything in their path. And yet, despite their terrifying power, they're also the architects of life itself, forging the elements that make up our very bodies in their fiery cores. This journey isn't just about size or brightness, it's about the raw, unbridled forces that shape existence. From hypergiants dwarfing our solar system to magnetars with magnetic fields strong enough to atomize you from thousands of light years away, each of these stars has earned its place among the universe's elite. So buckle up, we're about to venture into the heart of cosmic extremes where the laws of nature are pushed to their limits and the stars themselves become the stuff of legend. By the time we're done, you'll never look at the night sky the same way again. If our sun seems enormous, brace yourself because UY Scuti makes it look like a speck of dust. This colossal star isn't just big, it's a red hypergiant so vast that if you placed it at the center of our solar system, its outer layers would stretch beyond the orbit of Jupiter. Picture that for a moment, a single star swallowing up Mercury, Venus, Earth, Mars, and the asteroid belt without breaking a cosmic sweat. Found in the constellation Scutum, UY Scuti isn't just a record holder, it's a stellar anomaly. Its radius is over 1,700 times wider than our Sun's, making it one of the most immense objects ever discovered. But sheer size isn't its only claim to fame. This star burns with a terrifying brilliance, shining hundreds of thousands of times brighter than our Sun. If it were closer, its light would drown out every other star in our sky. Yet, like all giants, UY Scuti's story has an explosive ending. It's living on borrowed time, fusing elements at a frantic pace that can't last. In a few million years, a blink in cosmic terms, it will collapse under its own weight and detonate in a supernova so powerful it could outshine entire galaxies. The explosion will forge heavy elements like gold and uranium, scattering them across space to one day become part of new stars, planets, or even life. For now, UY Scuti stands as a humbling reminder of the universe's scale. It's not just a star, it's a cosmic titan rewriting what we thought possible. And as we'll soon see, it's just the first stop on our journey into the realm of stellar extremes. But even UY Scuti must bow to another celestial giant, VY Canis Majoris, a hypergiant so unstable and enormous it defies comprehension. Nestled in the constellation Canis Major, this star isn't just large, it's a cosmic maverick pulsating with violent eruptions and cloaked in a nebula of its own shredded remains. If placed at the center of our solar system, its surface would extend beyond Saturn's orbit, engulfing everything in its path. What makes VY Canis Majoris truly extraordinary isn't just its size, it's the star's turbulent personality. Unlike steady burning stars like our Sun, this hypergiant experiences wild brightness swings, dimming and flaring unpredictably as it ejects massive amounts of gas and dust into space. Astronomers have observed it shedding entire Jupiter-sized chunks of its atmosphere in violent outbursts, creating a sprawling nebula around it that glows with eerie beauty. Studying this star is like watching a dying firework, magnificent but chaotic, with eruptions so intense they distort our measurements. The challenges of observing VY Canis Majoris reveal just how extreme these cosmic giants can be. Its distance, about 3,900 light-years from Earth, means even our most powerful telescopes struggle to pierce through the thick clouds of dust it's expelled. Some scientists debate whether it's a single star or a complex multiple star system, further complicating our understanding. Yet amid the chaos, there's a strange elegance to its demise. The surrounding nebula, forged from centuries of eruptions, is a cosmic recycling plant scattering heavy elements that will one day birth new stars and planets. VY Canis Majoris reminds us that even in destruction, the universe creates, and as we'll soon discover, there are stars out there that wield power far beyond sheer size. While VY Canis Majoris dances on the edge of destruction, there's another cosmic heavyweight lurking much closer to home, Betelgeuse, the fiery shoulder of Orion. This isn't just any star, it's a ticking time bomb, a red supergiant so unstable that astronomers can practically hear its death throes echoing across the cosmos. Unlike the distant hypergiants we've explored, Betelgeuse sits a mere 600 light-years away, close enough that its eventual supernova could outshine the full moon in our night sky. What makes Betelgeuse so mesmerizing isn't just its inevitable demise, it's the star's eerie unpredictability. In late 2019, this cosmic beacon began dimming dramatically, losing nearly 2/3 of its brightness in a matter of months. For a moment, scientists wondered if it was about to explode. Telescopes scrambled to study it, revealing a startling explanation. Betelgeuse had coughed out a colossal cloud of dust, blocking its own light. It was as if the star had draped itself in a shroud, hinting at the chaos churning within. Peer deeper, and Betelgeuse's instability becomes even more fascinating. Its surface bubbles like a boiling cauldron, with massive plasma cells rising and falling in violent convection cycles. Some of these turbulent patches are so vast they could swallow our entire solar system. And then there's its shape. Betelgeuse isn't even a perfect sphere. Observations suggest it's slightly flattened, possibly due to rapid rotation or the gravitational tug of an unseen companion star. Yet for all its quirks, Betelgeuse's greatest spectacle is yet to come. When it finally explodes, whether tomorrow or 100,000 years from now, the blast will be visible even in broad daylight. The shockwave will flood nearby space with heavy elements, and for a brief, glorious moment, Orion will gain a brand new star in its constellation. Until then, Betelgeuse remains astronomy's ultimate reality check. A reminder that even the brightest giants are fleeting, and the universe loves a dramatic exit. But stellar power isn't just about size or explosions. As we'll soon discover, some stars wield forces so strange they bend the very laws of physics. If Betelgeuse is a ticking time bomb, Eta Carinae is a cosmic grenade that's already halfway through its blast, a binary star system so volatile it makes supernova look tame. Nestled in the Carinae constellation, this isn't just one star but two luminous monsters locked in a gravitational dance, each so massive they're tearing each other apart. Together, they shine over 5 million times brighter than our sun, but it's not their brilliance that makes them infamous, it's their temper. In the mid-1800s, Eta Carinae did something no astronomer had ever seen. It erupted. Not with a whimper, but with a cataclysm so violent it briefly became the second brightest star in the night sky. This wasn't a typical stellar flare. It was an explosion of incomprehensible scale, ejecting enough material to form 30 suns. The aftermath, a glowing, hourglass-shaped cloud of gas and dust called the Homunculus Nebula, which still expands outward at over 1 million miles per hour. Peer inside and you'll find the star system shrouded in chaos. its twin stars whipping around each other every 5.5 years in an orbit so close their stellar winds collide, sparking X-ray flares visible across the galaxy. What makes Eta Carinae truly terrifying is its instability. The primary star is a leviathan over 100 times the mass of our Sun, and it's shedding weight like a boxer before a title fight, hemorrhaging material in violent bursts. Scientists believe it's teetering on the edge of a hypernova, a supernova on steroids, which could unleash a gamma-ray burst intense enough to strip atmospheres from nearby planets. Yet, despite its fury, Eta Carinae is also a cosmic artist. The homunculus nebula glows with elements forged in its core: carbon, oxygen, iron, scattering the building blocks of future worlds into the void. For now, Eta Carinae remains a paradox, both a destroyer and a creator, a star system that defies every rule of stellar longevity. It's a reminder that in the universe's grand theater, the most powerful players don't just break the rules, they rewrite them mid-performance. And as we'll see next, there are stars out there that wield power not through explosions but through forces far more sinister. R136a1 isn't just another star. It's a cosmic heavyweight champion, the most massive star ever discovered, and it defies everything we thought we knew about stellar limits. Lurking in the heart of the Tarantula Nebula, a staggering 160,000 light-years from Earth, this monster tips the scales at over 250 times the mass of our Sun. To put that into perspective, if R136a1 replaced our Sun, its gravitational grip would warp the orbits of every planet in the solar system, and its searing radiation would sterilize any chance of life within thousands of light-years. What makes R136a1 truly mind-bending isn't just its size, it's the sheer energy it radiates. This star burns with the brightness of nearly 9 million suns, a luminosity so intense that it outshines entire star clusters. Peer at it through a telescope, and you're not just seeing a star, you're witnessing a thermonuclear furnace operating at the absolute edge of what physics allows. Yet, despite its unimaginable power, R136a1 shouldn't exist, at least not according to our old models of star formation. For decades, astronomers believed stars couldn't form with masses beyond about 150 suns. The math seemed clear: any larger, and the radiation pressure from a newborn star should blow away the surrounding gas before it could accumulate more mass. R136a1 shattered that assumption. Its existence forces us to rethink how stars are born, suggesting that in the densest stellar nurseries, like the Tarantula Nebula, chaos and competition might allow these extreme outliers to form. Some theories even propose that R136a1 could be the product of two massive stars merging, a violent cosmic collision that birthed this unparalleled titan. But don't expect R136a1 to stick around for long. Stars this massive live fast and die young, burning through their fuel at a breakneck pace. In just a few million years, a blink in cosmic terms, it will likely end its life in a spectacular supernova or even a hypernova, leaving behind a black hole as its final signature. Until then, it stands as a humbling reminder of the universe's capacity for extremes, pushing the boundaries of what we thought possible and challenging us to rewrite the rules of stellar physics. Yet, even R136a1 isn't the end of the story. The cosmos has other ways to redefine power, and our next stop introduces a star that doesn't just break records, it warps reality itself. WR102 isn't just hot. It's a stellar blowtorch, a Wolf-Rayet star so fierce it's literally evaporating into space. This cosmic powerhouse, located in the constellation Sagittarius, is one of the rarest and most extreme stars in our galaxy. Picture a star so violently unstable that it's shedding its own atmosphere at speeds exceeding 5 million miles per hour, fast enough to cross the entire United States in less than a second. That's the relentless fury of WR102, a star that's not just burning but disintegrating before our eyes. Wolf-Rayet stars like this one are the universe's ultimate high-speed self-destructors. Unlike the steady glow of our Sun, WR102 is cloaked in a searing hurricane of gas, its outer layers stripped away by radiation pressure so intense it creates a perpetual stellar wind. These winds aren't gentle breezes, they're supersonic tsunamis, blasting enough material into space each year to build several Earths. The result, a star shrouded in its own fiery wreckage, glowing with the eerie blue light of ionized helium and carbon forged in its core. But what truly sets WR102 apart is its temperature. With a surface hotter than 100,000 degrees Celsius, over 17 times scorchier than our Sun, this star doesn't just emit light, it bombards its surroundings with enough ultraviolet radiation to shred near-by molecules atom by atom. If you could somehow stand near it, which you absolutely couldn't, the sheer intensity of its heat would vaporize you before you even realized you were melting. All this chaos comes at a cost. WR102 is living on borrowed time, shedding so much mass that it's essentially committing stellar suicide. In just a few 100,000 years, a blink in cosmic terms, it will exhaust its fuel and detonate in a supernova so bright it could outshine its entire host galaxy. The explosion will forge heavy elements like gold and platinum, scattering them into the cosmos to one day become part of new planets or even life. Yet, even in death, WR102 refuses to go quietly. Some astronomers speculate its core might collapse directly into a black hole, leaving behind a gravitational tombstone as its final legacy. For now, WR102 serves as a stark reminder that in the universe, even the mightiest stars are fleeting. But as we'll soon discover, there are celestial forces out there that make this stellar hurricane seem almost tranquil by comparison. Hidden in the heart of the Milky Way, the Pistol Star doesn't just shine, it blazes with the fury of a cosmic flamethrower. This isn't your average luminous blue variable. It's a stellar rebel, a supermassive enigma so bright it outshines 10 million suns combined. Named for the pistol-shaped nebula it illuminates, this star is a celestial fireworks display, sculpting its surroundings with radiation so intense it carves voids in nearby gas clouds. What makes the Pistol Star truly extraordinary isn't just its brilliance, it's the sheer scale of its self-destruction. Every year, this star ejects enough material to build an entire planet, shedding mass with the violence of a perpetual stellar hurricane. Imagine a sun so unstable it's literally tearing itself apart, its outer layers hurled into space at speeds exceeding 6 million miles per hour. The result? A glowing halo of ejected gas, the Pistol Nebula, stretching over 4 light-years wide, a tombstone in the making. Yet for all its fury, the Pistol Star remains shrouded in mystery. Nestled deep in the galactic center, obscured by dust clouds, it took the Hubble Space Telescope to pierce through the cosmic smog and reveal its staggering luminosity. Even then, estimates of its size and mass vary wildly. Some calculations suggest it started life with over 200 times the mass of our Sun, placing it in the same league as R136a1. Others argue it's lighter but brighter, defying conventional stellar models. One theory even proposes it's not a single star but a binary system, its light amplified by a hidden companion. But the real puzzle lies in its origins. Stars this massive shouldn't form in isolation, yet the Pistol Star sits relatively alone, far from the dense clusters where stellar behemoths typically emerge. Did it wander here after a violent ejection from its birthplace, or is it the last survivor of a vanished stellar nursery? Every observation deepens the intrigue, painting a portrait of a star that refuses to fit neatly into our cosmic textbooks. Time is running out for this luminous rebel. In just a few million years, it's expected to collapse in a supernova so powerful it could rival the brightness of an entire galaxy. Until then, the pistol star serves as a dazzling reminder that even the most extreme corners of the universe still hold secrets, and sometimes the brightest flames burn the fastest. As we turn our gaze from this radiant spectacle, we'll encounter a star that wields a different kind of power, one not of light but of gravity. Rho Cassiopeiae isn't just another bright spot in the night sky, it's a ticking time bomb disguised in golden light. This yellow hypergiant, one of the rarest and most unstable stars known to science, glows with a deceptive calmness. Found in the constellation Cassiopeia, it's so colossal that if placed in our solar system, its surface would stretch beyond the orbit of Mars. But what makes Rho Cassiopeiae truly extraordinary isn't its size. It's the star's terrifying unpredictability, a celestial Jekyll and Hyde capable of violent transformations without warning. Unlike steady burning stars like our Sun, Rho Cassiopeiae wages an endless war against its own gravity. Its outer layers churn with turbulence, expanding and contracting like a cosmic heartbeat. This instability leads to eruptions so massive they dwarf anything in our solar system. In 2001, astronomers witnessed the star eject a colossal shell of material roughly 10,000 times the mass of Earth in a single outburst. That's the equivalent of 3,000 Mount Everests being hurled into space at once. The explosion was so powerful it temporarily dimmed the star's brightness, a telltale sign of its inner chaos. What's even more unsettling is Rho Cassiopeiae's identity crisis. Most stars spend their lives in predictable phases, but this hypergiant oscillates between classifications, sometimes appearing as a cooler red supergiant before heating back into a yellow hypergiant. These dramatic shifts reveal a star teetering on the edge of collapse, its core struggling to maintain equilibrium. Surface temperatures can swing by thousands of degrees in mere decades, a blink in stellar terms making it a nightmare for astronomers trying to pin down its behavior. Yet the most ominous detail lies in its future. Rho Cassiopeiae is a prime candidate for a core collapse supernova, an explosion so violent it could outshine entire galaxies for weeks. Given its distance only 8,000 light-years from Earth, the blast would be a celestial spectacle visible even in broad daylight. When it happens, the explosion will forge elements like gold and uranium, scattering them across the cosmos to one day seed new solar systems. For now, Rho Cassiopeiae remains a brilliant enigma, a reminder that the universe's most dazzling stars often harbor the darkest secrets, and as we'll soon see, the cosmos has even stranger ways to defy expectations. Mu Cephei doesn't just shine, it smolders like a dying ember in the cosmic dark, earning its nickname as the Garnet Star for its rich, ruby glow. Nestled in the constellation Cepheus, this crimson colossus is one of the largest stars ever discovered, so vast that if it replaced our Sun, its outer layers would swallow Jupiter whole. But what truly sets Mu Cephei apart isn't just its staggering size. It's the star's haunting beauty, a visual masterpiece that's captivated astronomers for centuries. Even through a small telescope, its deep red hue stands out like a drop of wine against black velvet, a color caused by complex molecules in its bloated atmosphere absorbing blue light. This star isn't just a pretty face, it's a cosmic powerhouse. Classified as a red hypergiant, Mu Cephei burns with a luminosity over 300,000 times greater than our Sun, a brilliance so intense it defies comprehension. Yet, despite its radiance, the star is remarkably unstable. Its brightness flickers unpredictably, dimming and flaring over periods ranging from months to years, a sign of its turbulent interior churning like a pot of molten lava. These pulsations aren't gentle, they're seismic upheavals causing the star's outer layers to expand and contract by millions of miles, ejecting massive plumes of gas into space with each convulsion. Mu Cephei's sheer scale is humbling. Estimates suggest its diameter could stretch to over 1 billion miles, large enough to fit the entire orbit of Saturn inside it. But like all hypergiants, this star is living on borrowed time. It's already in the final, violent throes of its life, fusing heavier and heavier elements in a desperate bid to stave off collapse. When it finally exhausts its fuel, Mu Cephei won't fade quietly. Instead, it will detonate in a supernova so spectacular it could outshine entire galaxies, scattering the elements forged in its core across the cosmos, elements that may one day seed new stars, planets, or even life. For now, the Garnet Star remains a jewel of the northern sky, a reminder that even in the vastness of space, beauty and destruction are often one and the same. And as we'll soon discover, the universe holds stars that wield power in ways far more mysterious than mere size or light. V838 Monocerotis didn't just flare up, it staged one of the most bizarre cosmic light shows ever witnessed. In early 2002, this previously unremarkable star in the constellation Monoceros suddenly exploded into brilliance, becoming 600,000 times brighter than our Sun in a matter of days. But this wasn't a typical supernova or even a stellar flare. Instead, V838 Mon unleashed something far stranger, a series of radiant pulses that illuminated vast shells of surrounding dust like a celestial strobe light, a phenomenon astronomers call light echoes. What makes this event so extraordinary isn't just the star's abrupt brightening, it's how the light behaved afterward. Unlike a supernova's shockwave, which races outward at thousands of miles per second, the glow from V838 Mon expanded leisurely, taking years to reveal intricate dust structures previously hidden in darkness. Hubble's breathtaking images captured this unfolding drama in unprecedented detail. Each new echo acted like a cosmic flashlight, progressively illuminating nested layers of interstellar material, some dating back thousands of years, transforming the region into a fleeting, ever-changing sculpture of light and shadow. At its peak, the spectacle resembled a glowing onion sliced open, with concentric rings of dust fluorescing in vivid blues and reds. Theories about what triggered this eruption are as wild as the event itself. Some suggest V838 Mon might have consumed nearby planets in a fit of stellar hunger, their icy or gaseous bodies triggering a temporary fusion frenzy. Others propose it's a rare merger burst, a cataclysmic collision between two stars that fused into one, releasing pent-up energy in a single, spectacular outburst. The most puzzling detail, after its dramatic flare, the star didn't die or collapse. Instead, it faded back into obscurity, leaving behind more questions than answers. What's undeniable is the legacy of those light echoes. By illuminating the surrounding interstellar medium, V838 Mon gave astronomers a novel way to map the galaxy's hidden architecture. The drifting dust clouds it revealed aren't just debris, they're the raw material for future stars and planets, a reminder that even the universe's most cryptic events can become tools for discovery. And as we'll see next, the cosmos has even stranger ways to bend the rules of physics. S Doradus doesn't just flicker, it throws cosmic tantrums, swinging between brilliance and obscurity with the unpredictability of a strobe light. This luminous blue variable, nestled in the Large Magellanic Cloud, is one of the most erratic stars ever observed, capable of brightening or dimming by a factor of 10 without warning. Imagine a star so volatile that its luminosity fluctuates enough to rewrite astronomy textbooks. That's S Doradus, a celestial enigma that defies every expectation of stellar stability. What makes this star so fascinating isn't just its mood swings, it's the sheer scale of its transformations. During its quiet phases, S Doradus shines with the brightness of several 100,000 suns. But when it erupts, it can surge to over 1 million times the luminosity of our own star, outshining entire star clusters in its host galaxy. These outbursts aren't mere flares, they're full-scale stellar rebellions where the star's outer layers balloon to staggering proportions, temporarily disguising it as a hypergiant before collapsing back into relative normalcy. The secret to S. Doradus's chaos lies in its delicate balancing act. Like a tightrope walker buffeted by hurricane winds, this star teeters on the edge of gravitational collapse. Its core generates so much radiation that the outer layers struggle to contain the pressure, leading to violent ejections of material. At times, it shrouds itself in a self-made cocoon of ejected gas, dimming its visible light while still raging beneath the surface. These episodes offer astronomers a rare glimpse into the final, turbulent stages of a massive star's life, a preview of what stars like Betelgeuse or Eta Carinae might eventually experience. But S. Doradus's greatest gift to science is its location. Floating in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, it provides a pristine laboratory for studying stellar evolution. Unlike stars in our own galaxy, which are often obscured by interstellar dust, S. Doradus sits in a relatively clear region, allowing telescopes to capture its tantrums in exquisite detail. Every eruption, every dimming phase, every ejected shell of gas adds another piece to the puzzle of how the universe's most massive stars live, die, and shape their surroundings. Yet for all we've learned, S. Doradus remains a master of suspense. Its next outburst could come tomorrow or a century from now, a reminder that in the cosmos, even the brightest stars play by their own rules. And as we'll soon see, the universe has even stranger ways to challenge our understanding of stellar power. Eta Carinae isn't just another bright spot in the cosmos, it's a celestial diva, a luminous blue variable star that stages explosive performances with the drama of a supernova and the longevity of a cosmic icon. Located in the constellation Carinae, this star commands attention not just for its brilliance shining up to 1 million times brighter than our Sun, but for the breathtaking nebula it sculpted from its own violent outbursts. Like an artist painting with stellar winds, Eta Carinae has surrounded itself with a glowing, intricate shell of gas and dust stretching over 5 light-years wide, a tapestry of its own turbulent past. What sets Eta Carinae apart isn't just its luminosity, it's the star's sheer unpredictability. Luminous blue variables are the rock stars of the stellar world, prone to wild mood swings in brightness and size. In the 1980s, Eta Carinae erupted in a cataclysm so immense it ejected roughly 10 times the mass of our Sun into space. Imagine a single star coughing up enough material to form 10 Jupiter-sized planets in one cosmic tantrum. The aftermath, a stunning nebula now illuminated by the star's relentless radiation, its filaments and knots glowing in vivid hues of blue and red, a fossil record of the star's violent mood swings. But the real mystery lies in Eta Carinae's balancing act. Stars this massive, tipping the scales at over 50 solar masses, walk a tightrope between gravity and radiation. Their cores generate so much energy that the outer layers are constantly on the verge of being blasted away. For Eta Carinae, this struggle manifests in dramatic expansions and contractions. At times, it swells to the size of Jupiter's orbit, its surface cooling and reddening like a dying ember. Then, without warning, it contracts violently, heating back up to searing blue-white temperatures. These swings aren't just aesthetic, they're survival mechanisms as the star fights to stabilize itself against total disintegration. Astronomers treasure Eta Carinae not just for its spectacle, but for the secrets it holds about stellar evolution. It's a living laboratory for understanding how the most massive stars in the universe cheat death for a while. Unlike supernova, which mark the end of a star's life, Eta Carinae's eruptions are rehearsals for destruction, offering a rare glimpse into the final, unstable chapters of a hypergiant's existence. Every outburst peels back another layer, revealing how these cosmic titans seed the universe with heavy elements and reshape their surroundings. Yet, even as we study it, Eta Carinae refuses to be pinned down. Recent observations suggest it might not be alone. Some researchers speculate it could have a hidden companion star, its gravitational tug adding to the chaos. Others debate whether its eruptions are truly random or follow some cryptic cycle. one thing's certain: when Eta Carinae finally exhausts its fuel, it won't fade quietly. It's destined to go out in a blaze of glory, likely collapsing into a black hole after one last, devastating supernova. Until then, it remains a masterclass in cosmic turbulence, a star that doesn't just defy expectations, it obliterates them. And as we'll soon discover, the universe has even stranger ways to push the limits of stellar power. P Cygni isn't just another bright star. It's a cosmic fingerprint, a blue hypergiant whose light tells a story of chaos and brilliance etched into its very spectrum. Found in the constellation Cygnus, this celestial anomaly isn't just notable for its size or luminosity. It's the star's light itself that holds the key to its strangeness. When astronomers first analyzed its spectrum in the 17th century, they discovered something unprecedented: bright emission lines paired with dark absorption shadows, a signature now known as the P Cygni profile. This unique pattern reveals a star hemorrhaging material at breakneck speeds, its outer layers accelerating away so violently that they create a stellar windscreen millions of miles thick. What makes P Cygni truly extraordinary is its history of outbursts like a stellar phoenix repeatedly rising from its own ashes. In the year 1600, this star erupted from obscurity, suddenly becoming one of the brightest objects in the night sky before fading again. Then, 3 decades later, it flared even more intensely, peaking at magnitude 3, visible to the naked eye despite lying over 5,000 light-years away. These weren't ordinary stellar flares. They were full-scale ejections of mass, violent tantrums that reshaped the star's surroundings and left astronomers puzzled for centuries. Today, we recognize these eruptions as the birth pangs of a hypergiant, a star so massive it teeters on the edge of stability, shedding entire suns' worth of material to avoid total collapse. Classifying P Cygni is like trying to pin down a shapeshifter. It's not just a blue hypergiant, it's a luminous blue variable, a rare breed of star that oscillates between periods of calm and cataclysm. Surface temperatures swing between 20,000 and 30,000 degrees Celsius, while its radius expands and contracts like a cosmic lung. At its largest, it could engulf the orbit of Mars, yet it's the star's instability that makes it invaluable to science. P Cygni serves as a living laboratory for studying mass loss, a process crucial to understanding how the universe's most massive stars evolve and how they seed galaxies with heavy elements. The star's true legacy, though, lies in its namesake spectral lines. The P Cygni profile has become a universal fingerprint for astrophysicists, a telltale sign of stars ejecting mass at extreme velocities. From supernova to quasars, this pattern appears wherever cosmic objects are tearing themselves apart, making P Cygni's influence far greater than its solitary light. It's a reminder that sometimes the most profound discoveries aren't just about what a star is, but what it teaches us about everything else. And as we'll soon see, the universe has even stranger ways to bend the rules of light and matter. VY Canis isn't just a star, it's a cosmic dance of extremes, a binary system where two stellar titans orbit each other in a mesmerizing display of contrast. At the center of this celestial waltz is an enormous red supergiant, so vast that if it replaced our Sun, its outer layers would stretch beyond the orbit of Jupiter. But what makes this system truly remarkable isn't just the primary star's staggering size. It's the smaller, hotter companion star that pirouettes around it, locked in a gravitational embrace that creates one of the most dramatic eclipses witnessed in the night sky. Every 20 years or so, VY Canis treats astronomers to a celestial spectacle, a month-long eclipse where the smaller, blue-white star vanishes behind the bloated disk of its red supergiant partner. But unlike the quick, predictable shadows cast by planets or moons, this eclipse unfolds in slow motion, stretching over nearly 2 years from start to finish. The reason: the sheer scale of the red supergiant, whose atmosphere is so tenuous and extended that the companion star doesn't just disappear, it fades gradually like a ship sinking into fog. As the smaller star moves behind its massive partner, its light filters through layers of ejected gas, revealing details about the supergiant's turbulent outer layers that would otherwise remain invisible. These eclipses are more than just cosmic theater, they're a goldmine for astronomers. By studying how the companion star's light changes as it passes behind the red supergiant, scientists can map the supergiant's atmosphere with incredible precision. They've discovered vast plumes of gas streaming into space, stellar winds so powerful they could strip entire planets of their atmospheres, and even hints of a circumstellar disk, a swirling ring of material that might one day birth new worlds. The smaller star, meanwhile, isn't just a passive participant. Its intense ultraviolet radiation ionizes the red supergiant's expelled gas, causing it to glow like a neon sign, a process that illuminates the complex dynamics between these two stellar giants. Yet for all its spectacle, VY Canis remains shrouded in mystery. The exact distance to this system is still debated, with estimates ranging from 2,000 to 5,000 light-years, making it difficult to pin down the star's true sizes and luminosities. Some observations even suggest the red supergiant might be pulsating, its radius swelling and contracting over time like a cosmic heartbeat. One thing's certain: when the next eclipse begins, likely around the year 2040, telescopes around the world will turn toward this stellar duo, eager to decode the secrets hidden in their shadow play. VY Canis reminds us that the universe's most captivating dramas often unfold in pairs, where the interplay between two stars can reveal far more than either could alone. And as we'll soon see, these binary systems are just the beginning when it comes to cosmic extremes. Antares burns like a fiery jewel in the heart of Scorpius, its deep red glow unmistakable even to the naked eye. This isn't just another bright star, it's a red supergiant so massive that if placed at the center of our solar system, its surface would stretch beyond the orbit of Mars, engulfing everything in its path. But what makes Antares truly fascinating isn't just its size, it's how eerily similar, and yet starkly different it is from Betelgeuse, its famous counterpart in Orion. Both stars are colossal, unstable, and destined for violent ends, but Antares harbors secrets that make it unique in the cosmic arena. While Betelgeuse dominates winter skies with its erratic dimming episodes, Antares holds court in summer, its name literally meaning rival of Mars for its blood-red hue. But appearances aside, these two supergiants are cosmic twins in many ways. Both are stars on borrowed time, their cores fusing heavier and heavier elements in a desperate bid to stave off collapse. Both shed material at staggering rates, cloaking themselves in vast nebulae of their own ejected gas. Yet Antares has a quieter intensity. Where Betelgeuse pulses with dramatic brightness changes, Antares fluctuates more subtly, its variations measured in years rather than months. Peer through a telescope and Antares reveals another surprise: its atmosphere. Unlike most stars whose surfaces appear crisp and defined, Antares' outer layers are so tenuous they resemble smoke, stretching millions of miles into space. Its photosphere, the visible surface we associate with stars, isn't a solid boundary but a hazy, roiling expanse where temperatures plummet and molecules form, something almost unheard of in stars of this class. This allows Antares to do something extraordinary: create dust in its own atmosphere. The same process that forms soot in a candle flame unfolds here on a cosmic scale, as carbon atoms link together in the star's cooler outer reaches, scattering its light into that signature ruby glow. But Antares' most dramatic chapter is yet to come. Like Betelgeuse, it's destined to explode as a supernova, an event that could happen tomorrow or 100,000 years from now. When it does, the blast will be visible even in daylight, outshining every star in our night sky combined. The explosion will forge elements like iron, silicon, and oxygen, building blocks for future planets and perhaps even life. Until then, Antares serves as a celestial time capsule, offering a glimpse into the final, volatile stages of a supergiant's life. And for those who know where to look, it's a reminder that even the most familiar stars hide universe-shaking power beneath their serene glow. Yet, as we'll soon discover, the cosmos has even stranger ways to defy expectation, stars that don't just burn bright but warp the very fabric of space itself. Rigel blazes like a sapphire torch at Orion's foot, a blue supergiant so luminous it outshines most stars in our galaxy. While Betelgeuse dominates the constellation with its ominous red glow, Rigel is its dazzling counterpart, a star radiating with 40,000 times the brightness of our Sun. Imagine a stellar furnace so intense that if it replaced our nearest star, its light would scorch Earth's surface to ash within seconds. Yet Rigel's brilliance isn't just about raw power. It's a celestial paradox, a star that burns furiously hot while hiding layers of complexity beneath its dazzling surface. What makes Rigel truly extraordinary is its hidden duality. To the naked eye, it appears as a single, unwavering point of light, but telescopes reveal it's actually a multiple star system. The primary star, Rigel A, is the blue supergiant we see, but it's gravitationally bound to at least 3 fainter companions. These lesser stars orbit at distances that would dwarf our entire solar system, their presence detectable only through subtle wobbles in Rigel's motion. This cosmic entourage adds intrigue to an already fascinating star, suggesting a turbulent history of stellar captures or perhaps even violent births. The contrast between Rigel and Betelgeuse couldn't be starker. While Betelgeuse is a bloated, unstable red supergiant nearing its explosive end, Rigel burns with the fierce energy of youth, its blue-white hue betraying surface temperatures nearly twice as scorching as our Sun's. Yet appearances can deceive. Rigel's vibrant color masks its own mortality. This star is likely only 8 to 10 million years old, a cosmic toddler compared to our Sun's 4.5 billion years, but it's already racing toward its demise. Blue supergiants live fast and die young, their enormous mass fueling nuclear reactions at a breakneck pace that exhausts their fuel in mere millions of years. Peering deeper, Rigel's influence extends far beyond its immediate surroundings. Its intense ultraviolet radiation ionizes nearby nebulae, including the Witch Head Nebula, which glows eerily under its stellar spotlight like a cosmic canvas illuminated by a celestial floodlight. This star doesn't just shine, it sculpts, its winds and radiation pressure carving cavities in interstellar gas clouds that might one day collapse into new stars. Even more intriguing is Rigel's variability. Unlike the dramatic dimming episodes of Betelgeuse, Rigel's brightness fluctuates subtly, a sign of its turbulent outer layers rippling with convection cycles larger than our entire solar system. For now, Rigel remains a beacon in Orion's saga, a star that embodies both beauty and transience. Its eventual fate, likely a spectacular supernova, will one day rewrite the constellation's familiar shape, but until then, it stands as a reminder that the universe's most dazzling lights often burn the shortest. And as we'll soon discover, some stars wield power not through brilliance alone, but by bending the very fabric of space-time. Deneb isn't just another bright dot in the night sky, it's a celestial lighthouse, a supergiant so luminous that it outshines nearly every other star in our galaxy despite being over 1,500 light-years away. To put that into perspective, if Deneb were as close to us as Sirius, just 8 light-years distant, it would cast shadows at night and outshine Venus, becoming the 3rd brightest object in our sky after the Sun and Moon. That's the staggering power of this cosmic beacon, a star that defies distance itself to dominate our summer nights as part of the iconic summer triangle. What makes Deneb truly extraordinary isn't just its brightness, it's the sheer scale of its energy output. Classified as an A-type supergiant, this star burns with the brilliance of nearly 200,000 suns, a luminosity so intense it challenges our understanding of stellar physics. Unlike most stars where brightness correlates closely with distance, Deneb's glow cuts through the cosmic void with ease, a testament to its monstrous size and furious energy production. Its surface temperature soars above 8,500 degrees Celsius, nearly twice as scorching as our Sun, bathing its surroundings in a harsh blue-white radiance that can be seen across interstellar space. But Deneb's role in the summer triangle adds another layer to its cosmic allure. Alongside Vega and Altair, it forms one of the most recognizable asterisms in the Northern Hemisphere, a celestial triad that has guided travelers and storytellers for millennia. While Vega and Altair are relatively close neighbors in cosmic terms, Deneb's extreme distance makes its prominence all the more impressive. It's like spotting a single lighthouse from across an ocean, its beam piercing the darkness while nearby harbor lights fade into insignificance. This trio isn't just a navigational aid, it's a cosmic coincidence, a chance alignment of three stellar titans from different corners of space, united in our sky by the quirks of perspective. Yet for all its brilliance, Deneb remains shrouded in mystery. Its exact distance has puzzled astronomers for decades. Estimates vary by hundreds of light years, making it difficult to pin down its true size and energy output. Some models suggest it could be one of the most massive stars known, with a radius nearly 200 times that of our Sun. Others propose it's in a rare transitional phase, having exhausted its core hydrogen and now fusing heavier elements in a desperate bid to stave off collapse. One thing's certain, Deneb's days are numbered. Supergiants like this live fast and die young, their enormous mass fueling runaway nuclear reactions that burn through their fuel in just a few million years. When Deneb finally meets its end, the explosion will be visible across the galaxy, a supernova so bright it could rival the full moon. Until then, this distant beacon serves as a reminder of the universe's capacity for extremes, a star whose light bridges unfathomable distances to spark wonder here on Earth. And as we'll soon see, the cosmos holds even more astonishing ways to redefine what we thought possible. Canopus commands the southern skies as a silent sentinel of celestial navigation, its brilliance second only to Sirius in the entire night sky. Shining with the luminosity of 15,000 suns, this golden-white supergiant dominates the constellation Carinae, visible to nearly two-thirds of Earth's population, yet strangely overlooked in popular culture. Its radiance isn't just for show. For centuries, Canopus served as a cosmic compass for sailors navigating the treacherous waters below the equator, its steady glow cutting through atmospheric turbulence better than almost any other star. Spacecraft like Voyager and Cassini still use it today as a guiding beacon, its unwavering position helping to calibrate instruments across the solar system. So why does this stellar giant linger in relative obscurity? The answer lies in geography and timing. Unlike Sirius, which dominates winter skies across the northern hemisphere, Canopus remains invisible above latitudes like New York or Tokyo, hugging the southern horizon where light pollution often drowns it out. Even when visible, it lacks the mythological fanfare of Orion or the North Star, its name derived from a forgotten Greek navigator whispering history rather than legend. Modern stargazers might overlook it simply because it never rises high enough to dominate the night, often mistaken for a bright planet or obscured by Earth's murky atmosphere near the horizon. Yet Canopus holds secrets that defy its quiet reputation. This star is a cosmic chameleon, classified as an F-type supergiant, a rare breed that bridges the gap between yellow and white stars. Its surface burns at a peculiar 7,000 degrees Celsius, cooler than blue giants like Rigel but hotter than our Sun, giving it that distinctive golden hue. What truly sets Canopus apart is its life cycle. It's likely a former blue supergiant that exhausted its core hydrogen and expanded, now fusing helium in a volatile phase that precedes a dramatic transformation. In astronomical terms, it's living on borrowed time, destined to shed its outer layers and collapse into a dense white dwarf. the star's influence extends far beyond navigation. Telescopes reveal it surrounded by a vast infrared halo, likely debris from ancient eruptions or a circumstellar disk, evidence of its turbulent evolution. Some theories even suggest Canopus might have a hidden companion, its gravitational tug subtly altering the star's motion. For now, this celestial titan remains a paradox, a star bright enough to guide interstellar missions yet humble enough to evade casual notice, a reminder that brilliance doesn't always demand attention. And as we venture further into the cosmos, we'll encounter stars that wield power in ways far beyond mere light forces that twist space and time themselves. Sirius isn't just the brightest star in our night sky, it's a celestial powerhouse with a hidden twin and a cultural legacy spanning millennia. Gleaming in the constellation Canis Major like a diamond against black velvet, this star outshines every other in Earth's heavens, its brilliance amplified by its relatively close proximity of just 8.6 light-years. But what makes Sirius truly fascinating isn't just its luminosity. It's the cosmic dance it performs with an invisible partner, a white dwarf so dense it packs the mass of our Sun into an object the size of Earth. Together, they form a binary system that's rewritten our understanding of stellar evolution. For centuries, astronomers puzzled over subtle wobbles in Sirius's motion, as if an unseen hand were tugging at it. In 1862, that mystery was solved. Sirius B, the first white dwarf ever discovered, revealed itself through a telescope. This stellar ghost is the corpse of what was once a massive star, now collapsed into a smoldering ember so dense that a sugar cube-sized chunk would weigh more than a ton on Earth. The contrast between the two stars couldn't be starker. Sirius ablaze with blue-white intensity, 25 times brighter than our Sun, while its companion emits a faint, eerie glow, the last whispers of a star that burned out long ago. Their orbital tango takes 50 years to complete, with Sirius B swinging as close as Neptune's orbit from its dazzling partner before hurtling back out into the void. Yet Sirius's influence extends far beyond astrophysics. This star has woven itself into human history like no other. Ancient Egyptians aligned their temples with its heliacal rising, marking the annual flooding of the Nile and the promise of fertile soil. Polynesian navigators used it as a guiding beacon to traverse the Pacific, while Greek poets warned of its scorching summer appearance, linking it to the dog days that still bear its name today. Even modern conspiracy theories swirl around Sirius, from claims of alien contact to pseudoscientific myths, proof that its brilliance still ignites our imaginations. What's often overlooked is Sirius's role as a cosmic Rosetta Stone. Studying its white dwarf companion helped astronomers confirm Einstein's theory of general relativity, as the star's intense gravity bends light precisely as predicted. Today, Sirius B serves as a laboratory for extreme physics, where matter behaves in ways impossible to replicate on Earth. Meanwhile, Sirius A continues to challenge assumptions. Its metallic composition suggests it may have swallowed planets or absorbed a sibling star in its youth. As we gaze at Sirius tonight, we're not just seeing a pretty light, we're witnessing a stellar partnership that's shaped both the cosmos and human culture. A reminder that sometimes the brightest stars hide the darkest secrets. Vega spins so fast it's nearly tearing itself apart, a celestial speed demon whirling at over 270 kilometers per second at its equator, completing a full rotation every 12.5 hours. Compare that to our Sun's leisurely 25-day spin, and you'll understand why Vega isn't just another bright dot in Lyra. This star's furious rotation flattens it like a cosmic pancake, its equator bulging outward while its poles squeeze inward, creating a temperature difference of nearly 2,000 degrees Celsius from its cooler equator to its scorching poles. That extreme shape isn't just a curiosity, it's a window into how stars evolve under forces that would rip lesser objects apart. For astronomers, Vega is more than a spinning marvel, it's the gold standard for measuring stellar brightness. Back in the 19th century, it became the baseline for the magnitude scale, the ruler by which we gauge every other star's luminosity. Today, its steady, well-understood light serves as a calibration point for telescopes across the electromagnetic spectrum, from radio waves to X-rays. But Vega's reliability hides a surprise. It's not as stable as we once thought. Recent studies reveal subtle pulsations, tiny brightness fluctuations that hint at complex processes churning beneath its radiant surface. Perhaps Vega's greatest intrigue lies in what surrounds it, a vast, dusty debris disk, the aftermath of violent cosmic collisions. This sprawling ring of asteroids and comets stretches hundreds of astronomical units into space, glowing faintly in infrared light. Within that chaos, astronomers have spotted tantalizing gaps and clumps, possible fingerprints of planets carving paths through the wreckage. While no world has been confirmed yet, the evidence suggests Vega's system could mirror our own solar system in its youth, when fledgling planets bulldozed through primordial dust. The real kicker, Vega's story is just beginning. At only 450 million years old, a tenth of our sun's age, this star burns hotter and dies faster, destined to exhaust its fuel in another 500 million years. By then, its debris disk may have coalesced into new worlds, its legacy written not just in light, but in the birth of fresh solar systems. For now, Vega remains a celestial benchmark, a reminder that sometimes the stars we rely on to measure the universe are the ones hiding the most explosive secrets. Polaris doesn't just guide travelers, it holds the sky steady, the unwavering anchor around which the northern heavens slowly turn. For centuries, sailors, explorers, and even migrating animals have relied on this star's fixed position above Earth's North Pole, a celestial lighthouse shining with reassuring constancy. But beneath its tranquil reputation lies a surprising truth. Polaris isn't a single star, nor is it truly motionless. It's a complex triple-star system, with the primary Polaris R stealing the spotlight as both a navigational icon and a pulsating Cepheids variable, a cosmic metronome whose rhythmic brightness changes help astronomers measure the universe's vast distances. What makes Polaris R extraordinary is its heartbeat-like variability. Every 4 days, this yellow supergiant swells and contracts, its diameter fluctuating by millions of miles as its outer layers dance to the tune of internal pressure and gravity. These pulsations cause its brightness to rise and fall by about 15%, a pattern so reliable that astronomers once called Cepheids the yardsticks of the cosmos. By comparing Polaris's intrinsic brightness to its apparent glow in our sky, scientists can calculate its distance with remarkable precision, about 430 light-years from Earth. But here's the twist: Polaris is a weird Cepheid. While most stars in this class grow more variable over time, Polaris's pulsations have weakened over the last century, its fluctuations becoming almost imperceptible by the 1990s before subtly strengthening again. Some theories suggest it might be transitioning out of its Cepheid phase entirely, making it a rare glimpse into stellar evolution in action. Now let's talk about the rest of the family. Polaris B, a main sequence star about 1.4 times the Sun's mass, orbits its brilliant sibling at a distance of about 2,400 astronomical units, so far that it takes tens of thousands of years to complete a single revolution. Then there's Polaris AB, the elusive third member of this stellar trio. This dwarf star hugs Polaris R in a tight orbit, completing a circuit every 30 years, but it's so close and faint that it wasn't directly observed until 2006, when the Hubble Space Telescope finally pierced the glare of its dominant partner. Yet for all its scientific intrigue, Polaris's greatest legacy remains its role as humanity's steadfast guide. Unlike other stars that rise and set, Polaris holds its position in the sky because Earth's rotational axis points almost directly at it, a fluke of cosmic geometry that won't last forever. Thanks to the slow wobble of our planet's axis called precession, the title of North Star will pass to Gamma Cephei in about 1,000 years, then eventually to brilliant Vega in 12,000. Polaris's reign is temporary, but for now it remains a silent sentinel, a reminder that even the most familiar stars are full of secrets. And as we'll see next, the universe has even stranger ways to bend the rules of navigation. Alpha Centauri isn't just a twinkle in the southern skies, it's our solar system's next-door neighbor, a cosmic stone's throw away at just 4.37 light-years. But this stellar system hides a twist. What appears as a single star to the naked eye is actually a tangled trio, locked in an intricate gravitational dance that's reshaped our understanding of nearby space. The brightest pair, Alpha Centauri A and B, orbit each other every 80 years like stellar partners in a celestial waltz, their separation varying from roughly Saturn's to Pluto's distance from our Sun. Meanwhile, Proxima Centauri, the third member, lurks in the shadows, a dim red dwarf so far from its siblings it takes over 500,000 years to complete a single orbit around them. What makes this system extraordinary isn't just its proximity, it's the tantalizing possibility of habitable worlds. In 2016, astronomers discovered Proxima b, an Earth-sized planet nestled snugly in Proxima Centauri's Goldilocks zone, where liquid water could exist. Though bathed in the red dwarf's intense flares, this rocky world ignited imagination's worldwide proof that potentially life-friendly planets might exist right on our cosmic doorstep. But the surprises didn't stop there. Recent studies suggest Alpha Centauri A and B could host their own planets, warm, sunlit worlds where conditions might be even more favorable for life as we know it. Picture an exoplanet orbiting Alpha Centauri A, basking in sunlight nearly identical to our own, or a world circling Alpha Centauri B, watching twin suns rise and set in its skies. The intrigue deepens when we examine these stars individually. Alpha Centauri is a near twin of our Sun, same spectral type, similar temperature, even matching metallicity, making it the most familiar star beyond our solar system. Its companion, Alpha Centauri b, is slightly cooler and smaller, an orange-hued counterpart that shares its stable, middle-aged phase. Together, they form one of the most stable binary systems known, their gravitational interplay gentle enough that planets could theoretically survive in their orbits. Proxima, by contrast, is a tempestuous toddler, a flare star prone to violent outbursts that would strip atmospheres from nearby planets in seconds. Yet its faint glow and compact size make it the star most likely to host planets we could study in detail, worlds close enough that future telescopes might analyze their atmospheres for signs of life. Humanity's fascination with Alpha Centauri isn't just scientific, it's woven into our dreams of interstellar travel. This system is the target of Breakthrough Starshot, an ambitious project aiming to send microchip-sized probes there within our lifetimes, propelled by Earth-based lasers. At 20% light speed, these tiny travelers could reach Alpha Centauri in just 20 years, beaming back images of alien worlds before today's children reach middle age. The very idea transforms this star system from a distant point of light into a tangible destination, a beachhead for humanity's first steps beyond our solar cradle. As we peer at Alpha Centauri tonight, we're not just seeing stars, we're gazing at possibilities. Whether as a laboratory for exoplanet studies, a testing ground for new physics, or someday, a second home for our species, this triple star system reminds us that the universe's greatest adventures might lie closer than we ever imagined. And as we'll soon discover, even familiar stars can harbor surprises that rewrite the rules of cosmic neighborhoods. Proxima Centauri may be the closest star to our Sun, but don't let its proximity fool you. This dim red dwarf is anything but ordinary. Tucked away in the constellation Centaurus, just 4.24 light-years from Earth, this tiny star weighs in at barely 12% of our Sun's mass and glows with a feeble reddish hue, so faint it's invisible to the naked eye from most locations. Yet within its modest frame lies a cosmic paradox. While red dwarfs like Proxima are the most common stars in the galaxy, their very nature makes them both tantalizing and treacherous for astronomers seeking alien worlds. The discovery of Proxima b in 2016 sent shockwaves through the scientific community, a rocky planet roughly Earth-size orbiting snugly within its star's habitable zone. On paper, it's the stuff of science fiction, a nearby world where liquid water could theoretically pool on the surface, but the reality is far more complex. Proxima Centauri's habitable zone is a far cry from the gentle, sun-drenched region we're familiar with. Because the star is so cool and dim, Proxima b huddles just 7.5 million kilometers away, 20 times closer than Earth orbits the Sun. This proximity locks the planet in a gravitational embrace so tight a year there lasts a mere 11 Earth days. Worse yet, tidal forces likely render Proxima b tidally locked, with one hemisphere perpetually scorched by daylight while the other languishes in eternal night. But the real challenge comes from Proxima Centauri's volatile temper. Unlike our steady sun, this red dwarf is a flare star, prone to violent eruptions that can double its brightness in minutes. These solar tantrums blast the system with X-rays and ultraviolet radiation at levels hundreds of times stronger than Earth receives, enough to strip atmospheres and sterilize surfaces. Recent studies suggest Proxima b might endure stellar flares so intense they deliver the equivalent of 4,000 years' worth of Earth UV radiation in just 10 seconds. For any hopeful microbes clinging to existence there, survival would require sheltering deep underground or beneath global ice sheets far from the star's wrath. Observing Proxima Centauri and its planetary companion pushes our technology to the limits. The star's faintness means detecting subtle wobbles from orbiting planets. The gold standard for exoplanet discovery requires precision instruments like the espresso spectrograph. Even then, Proxima's flares create noise that can mask planetary signals, forcing astronomers to develop new algorithms to filter out the chaos. Meanwhile, direct imaging of Proxima b remains impossible with current telescopes. Its proximity to the star drowns it in glare, like trying to spot a firefly hovering near a spotlight. Yet for all its hostility, Proxima Centauri offers an irresistible opportunity. Its record-breaking proximity makes it the prime target for future interstellar missions, like Breakthrough Starshot's ambitious plan to send laser-propelled microprobes there within decades. And while Proxima b may not be the Earth twin we envisioned, its existence proves that even the most unassuming stars can host worlds, perhaps ones with conditions we've yet to imagine. As we continue to study this tempestuous neighbor, we're not just exploring a star, we're testing the boundaries of what habitable really means in a universe full of surprises. Barnard's star doesn't just drift lazily across the cosmos, it races through the void like a cosmic bullet, darting faster against the backdrop of distant stars than any other known stellar neighbor. While most stars appear fixed in their constellations over human timescales, this faint red dwarf tears through space at a blistering 140 kilometers per second, covering the width of a full moon in the night sky every 180 years. That might not sound like much, but for astronomers, it's like watching a sprinter in a crowd of statues, a star so restless it earned its own runaway nickname, Barnard's runaway star. What makes this speedster truly remarkable isn't just its velocity, it's the tantalizing possibility of hidden worlds. For decades, Barnard's star captivated scientists as a prime candidate for exoplanets, its proximity just 6 light-years away making it an ideal laboratory for detection. The star's dim glow, emitting only 4/10,000ths of our sun's luminosity, should have made spotting tiny planetary wobbles easier, yet the hunt has been fraught with false hopes. In the 1960s, astronomer Peter van der Kamp famously claimed to detect 2 gas giants orbiting Barnard's star based on subtle telescope movements, only for later analysis to reveal the signals were artifacts of equipment changes. The disappointment lingered for half a century until 2018, when new data suggested a frigid super-Earth might indeed lurk in the system, a frozen world 3 times Earth's mass, locked in a 233-day orbit. Even if confirmed, Barnard's star B would be a harsh place. Bathed in feeble starlight, its surface likely hovers around -170 degrees Celsius, colder than Jupiter's icy moon Europa. With no atmosphere thick enough to trap heat and a star prone to violent flares, this isn't the habitable oasis we once dreamed of. Yet its very existence hints at a broader truth. Even ancient, quiet stars like Barnard's, estimated at 10 billion years old, twice the age of our Sun, might still cradle planets in their gravitational grip. Beyond its planetary potential, Barnard's star serves as a cosmic time capsule. Its advanced age means it formed when the universe was still seeding its first generations of stars, carrying a chemical fingerprint of that primordial era. Unlike younger, metal-rich stars, Barnard's is a population Roman II relic, deficient in heavy elements forged by later supernova. Studying it offers clues to what the earliest stellar neighborhoods might have looked like and how planets could form in such sparse environments. For now, Barnard's star continues its solitary sprint, destined to become our Sun's closest stellar neighbor in just 10,000 years, passing within 4 light-years before fading again into the galactic dark. Whether it carries frozen worlds or not, this speedy red dwarf reminds us that even the quietest stars can hold secrets, and sometimes the most unassuming objects in the night sky are the ones racing toward the future the fastest. Wolf 359 may be one of our closest stellar neighbors at just 7.8 light-years away, but don't expect to spot it on a casual evening stroll. This red dwarf glows so dimly you'd need a telescope to catch its faint, ruby flicker in the constellation Leo. Shining with less than 1% of our Sun's luminosity, Wolf 359 is the kind of star that hides in plain sight, invisible to ancient astronomers yet oddly famous in modern pop culture. Sci-fi fans might recognize its name from Star Trek, where it hosted a pivotal battle against the Borg, or from countless novels where it's portrayed as a waypoint for interstellar travelers. But the reality of this unassuming star is far more fascinating than fiction. Beneath its quiet exterior, Wolf 359 is a cosmic powder keg. Like many red dwarfs, it's prone to violent flare activity, sudden bursts of radiation that can catapult its brightness tenfold in minutes. These aren't gentle solar flickers, they're cataclysmic eruptions strong enough to strip atmospheres from any nearby planets. In 2019, astronomers caught Wolf 359 in the act, recording a flare so powerful it briefly outshone the star's usual glow by a factor of 40. Unleashing enough X-rays to fry an Earth-like world's surface in hours. What makes these eruptions especially dangerous is their frequency. Unlike our Sun, which might unleash a major flare once a century, Wolf 339 averages several per day, bathing its surroundings in a relentless storm of high-energy particles. Yet despite this hostility, scientists haven't given up on the idea of habitable worlds here. Red dwarfs like Wolf 359 burn so slowly they could theoretically host planets for trillions of years, far longer than the universe's current age. The trick is surviving their fiery youth. Some theories suggest that planets forming in the habitable zone, so close they'd orbit in mere Earth days, might develop thick atmospheres or global magnetic fields to shield against radiation. Others propose life could thrive underground or beneath ice sheets, sheltered from the star's wrath. Even more intriguing is the possibility of tidally locked planets, where one side eternally faces the star while the other freezes in darkness. The boundary between these extremes, known as the Terminator line, could offer a narrow band of temperate conditions, a twilight zone where liquid water might persist. Wolf 359 mysteries don't end there. Recent studies hint at a possible Jupiter-sized planet orbiting at a chilly distance, though confirming it has been tricky. The star's faintness makes detecting subtle planetary wobbles a challenge, and its flares create noise that can mask signals. Still, the hunt continues, fueled by the tantalizing prospect of finding worlds around one of our nearest stellar neighbors. Whether it hosts planets or not, Wolf 359 serves as a humbling reminder. Sometimes the universe's most unremarkable stars hide the most explosive secrets and the wildest possibilities. TRAPPIST-1 may be small, so dim it's invisible without a telescope, but this ultra-cool red dwarf is home to one of the most tantalizing planetary systems ever discovered. Tucked away in the constellation Aquarius, about 40 light-years from Earth, this star barely reaches the size of Jupiter and glows with a feeble reddish hue, its surface temperature a chilly 2,500 degrees Celsius. Yet what it lacks in brilliance, it makes up for in cosmic real estate. TRAPPIST-1 hosts 7 Earth-sized worlds, all packed into orbits tighter than Mercury's, turning this unassuming star into a laboratory for alien life. The discovery of these planets in 2017 sent shockwaves through astronomy. Here was a system where rocky worlds outnumbered our own solar system's terrestrial planets, all orbiting a star that could outlive the universe itself. Red dwarfs like TRAPPIST-1 burn their fuel so slowly they'll shine for trillions of years long after stars like our Sun have flickered out. That means any life emerging here would have an almost unimaginable head start. But the real magic lies in the arrangement of these worlds. 3 TRAPPIST-1e, F, and G sit squarely in the habitable zone where temperatures might allow liquid water to pool on their surfaces. Imagine standing on TRAPPIST-1e, the most Earth-like of the bunch. The sky would glow a perpetual twilight red, the star hanging like a dim ember overhead, appearing 3 times larger than our Sun despite its faintness. With years lasting just 6 Earth days, seasons would blur together in a rapid cycle. And because the planets are so close together, neighboring worlds would dominate the skyline, some looming as large as our moon, their cratered surfaces or swirling atmospheres visible to the naked eye. Yet the very features that make TRAPPIST-1 intriguing also pose challenges. Such proximity to their star likely locks these planets tidally, forcing one side into endless daylight and the other into eternal night. Without atmospheric circulation, the day side might scorch while the night side freezes, leaving only a narrow twilight strip hospitable to life. Worse, red dwarfs are notorious for violent flares, and TRAPPIST-1 is no exception. In 2016, just months before its planets were discovered, the star unleashed a flare that briefly doubled its brightness, a surge of radiation that could have stripped atmospheres or sterilized surfaces. Still, hope persists. Some models suggest TRAPPIST-1 planets could have thick atmospheres or global oceans that distribute heat, mitigating the extremes of tidal locking. Others propose that frequent volcanism driven by gravitational squeezing from their star might replenish atmospheres faster than flares can erode them. The James Webb Space Telescope has already begun probing these worlds for atmospheric hints, searching for molecules like carbon dioxide or methane that could signal geological or even biological activity. What makes TRAPPIST-1 truly revolutionary isn't just the possibility of life, it's the accessibility of its secrets. Most exoplanets we found orbit stars too bright to study in detail, their planetary signals drowned in glare. But TRAPPIST-1 faintness allows telescopes to scrutinize its worlds with unprecedented clarity. Each transit, when a planet crosses the star's face, is a miniature eclipse filtering the star's light through any atmosphere present like a cosmic stained glass window. Whether TRAPPIST-1 planets are barren rocks or teeming with life, they've already reshaped our cosmic perspective. They prove that even the smallest, coldest stars can host intricate planetary systems worlds that might outlast every civilization humanity ever builds. And as we turn our gaze to the next stellar marvel, we're reminded that the universe's quietest corners often hold the loudest surprises. Kepler 444 isn't just old, it's a cosmic fossil, a star that was already ancient when Earth formed. Born over 11 billion years ago, this orange-hued dwarf has been shining since the universe was just 2 billion years young, making it one of the oldest known stars with a planetary entourage. Nestled in the constellation Lyra, about 117 light-years away, Kepler 444 isn't much to look at, smaller and cooler than our Sun, with just 70% of its mass. But what it lacks in size, it makes up for in historical significance. This star doesn't just host planets, it rewrote our understanding of when planets could first appear in the cosmos. The real marvel lies in its 5 rocky worlds, each crammed into orbits tighter than Mercury's. Discovered by NASA Kepler spacecraft in 2015, these planets are all roughly Earth-sized or smaller, with the innermost completing a full orbit in less than 10 days and the outermost in just 45. Picture a solar system where you could hop between planets in weeks, their surfaces baked by the relentless glow of their aging sun. But don't mistake these worlds for potential havens. Their proximity to Kepler 444 means they're roasted to extremes, their surfaces likely molten or stripped of any early atmospheres by billions of years of stellar radiation. What makes these planets revolutionary isn't their habitability, it's their existence at all. Before Kepler 444, we assumed rocky planets needed heavy elements like iron and silicon, which were scarce in the early universe. Yet here they are, fully formed when the Milky Way was still in its infancy, proving that planet building began far earlier than anyone predicted. These worlds coalesced from a protoplanetary disk enriched by just a fraction of the metals found in our solar system, suggesting the recipe for rocky planets is more flexible and universal than we imagined. Studying this system is like peering into a cosmic time capsule. Kepler 444 planets likely formed during the era when the first galactic structures were taking shape, their birth predating Earth by a staggering 6 to 7 billion years. If rocks could talk, these worlds would whisper secrets from an epoch when the universe was still assembling its first generations of stars. Their very presence hints that life's building blocks, water, organic molecules, stable orbits might have existed far longer than we ever suspected, stretching the timeline for potential life's emergence back into the depths of cosmic history. Yet Kepler 444's story isn't just about age, it's about survival. This star has burned through 2/3 of the universe's lifetime, its planets enduring unimaginable stretches of cosmic time. While their surfaces may be barren now, their longevity hints at a tantalizing possibility. If rocky worlds could form so early, perhaps others in more temperate zones did too, worlds that had billions of years more than Earth to nurture life. As we continue to search for ancient planetary systems, Kepler 444 stands as a beacon, reminding us that the universe's history is written not just in stars, but in the silent, enduring worlds that circle them. T-Tauri stars are the cosmic equivalent of newborn stellar infants still wrapped in the swirling blankets of gas and dust from which they formed. These young stellar objects represent a fleeting but crucial phase in a star's life, caught between the collapse of a molecular cloud and the ignition of stable nuclear fusion in their cores. One of the most famous examples, T-Tauri itself, flickers in the constellation Taurus like a restless child, its brightness swinging unpredictably over days or weeks. This variability isn't just random chaos, it's the astrophysical signature of a star still learning to control its own energy, with magnetic fields twisting like tantrums and surface spots larger than entire solar systems. What makes these stars so invaluable to astronomers isn't just their youth, it's the treasure trove of planetary raw materials orbiting them. Nearly all T-Tauri stars are encircled by thick protoplanetary disks, vast rings of dust and gas where fledgling planets assemble. These disks can stretch hundreds of astronomical units across, containing enough material to build entire solar systems. The Hubble Space Telescope has captured stunning images of these nurseries, revealing dark lanes where infant planets may already be carving their first paths. Some disks even show concentric gaps, cosmic construction zones where budding worlds are sweeping up debris like celestial bulldozers. The sheer violence of a T-Tauri star's environment defies imagination. Powerful stellar winds scream outward at supersonic speeds, while magnetic fields funnel material into colossal eruptions called Herbig-Haro jets. These plasma beams, often spanning light years, act like escape valves for excess energy, shooting out from the star's poles at hundreds of kilometers per second. Witnessing these jets is like watching a stellar birth cry a fiery announcement of a new presence in the galaxy. Yet amid this chaos, the delicate process of planet formation persists. Dust grains collide and stick together, growing from microscopic specks into mountain-sized planetesimals, all while bathed in the harsh ultraviolet glow of their tempestuous parent star. For astronomers, T-Tauri stars offer something rare, a front-row seat to cosmic creation. By studying their flickering light, scientists can measure accretion rates, how quickly the star gathers material from its disk, and even detect the gravitational footprints of hidden protoplanets. Infrared telescopes peer through the dust to map temperature variations in the disks, revealing potential nurseries for gas giants or icy worlds. Even their chemical composition holds clues. Many T-Tauri systems show abundant organic molecules, the same building blocks that likely seeded life on Earth. Yet these stellar toddlers won't stay this way for long. In just 10 to 100 million years, a blink in cosmic time, T-Tauri stars will settle into the stable hydrogen-burning phase that defines stars like our Sun. Their disks will dissipate, either consumed by the star or forged into planets, leaving behind mature solar systems. For now, their turbulence and brilliance serve as a reminder. The universe's most transformative moments often happen in the nursery. And as we'll see next, not all young stars follow the same path to maturity. Epsilon Aurigae doesn't just dim, it vanishes. Every 27 years, like clockwork, this bright star in the constellation Auriga fades to nearly half its usual brightness, remaining eclipsed for an astonishing 2 years before slowly rebounding. These bizarre marathon eclipses have puzzled astronomers since the 19th century, turning Epsilon Aurigae into one of the most enigmatic binary systems in our galaxy. Unlike typical eclipsing stars that wink in and out over days or weeks, this celestial oddity operates on a timescale that feels almost geological, its companion hiding a secret so profound it's taken over a century to unravel even part of the mystery. The heart of the puzzle lies in what's blocking the light. Most eclipsing binaries involve two stars passing in front of each other, but Epsilon Aurigae's companion defies expectation. It's invisible. For decades, theories ranged from a black hole to a bizarre dark star until modern telescopes peeled back the layers of this cosmic onion, the culprit. A colossal disk of opaque dust stretching billions of miles wide, orbiting an unseen central object, likely a dying star shrouded in its own debris. Picture a cosmic vinyl record spinning edge on from our perspective, its dark material blotting out Epsilon Aurigae's glow like a celestial thumb pressed against a flashlight. What makes this system truly mind-bending is the disk's staggering scale. If placed in our solar system, it would extend from the Sun past Uranus, its outer reaches frigid and sparse while its inner regions glow faintly with the heat of their hidden engine. Even more perplexing is how such a fragile structure survives intact over its 27-year orbit. Some models suggest the central object, possibly a hot, young star or a cooling stellar remnant, generates just enough gravity to shepherd the dust, while others propose magnetic fields act as invisible scaffolding. The most recent eclipse from 2009 to 2011 armed astronomers with tools their predecessors couldn't dream of: infrared imagers, spectrographs, and interferometers that mapped the disk structure in unprecedented detail. These observations revealed something even stranger. Halfway through the eclipse, Epsilon Aurigae's light briefly brightened, as if peeking through a keyhole in the disk. This unexpected flicker hinted at a hollow center, a gap in the dust possibly cleared by an unseen planet or the gravitational tug of the central object. Yet for every answer, Epsilon Aurigae spawns new questions. Why does the system emit more infrared light than expected, suggesting hidden heat sources? Could there be multiple objects embedded in the disk, and what forged this structure in the first place, a catastrophic collision or the slow death throes of a star? The next eclipse around 2036 may finally crack these riddles, but until then, Epsilon Aurigae stands as a testament to the universe's flair for drama. It's not just a star, it's a cosmic detective story, one where the clues unfold not in pages but in decades. And as we'll soon discover, even systems like this are just the beginning when it comes to celestial mysteries. Tabby's star doesn't just dim, it flickers like a cosmic light bulb with a faulty switch, plunging into unpredictable dips in brightness that defy conventional explanation. Officially known as KIC 8,462,852, this unassuming star in the constellation Cygnus first made headlines in 2015 when astronomers discovered its light had dropped by staggering 22% at times, a fluctuation unlike anything seen in ordinary stars. For comparison, even a Jupiter-sized planet transiting a star causes a dimming of barely 1%. Tabby's star wasn't just breaking the rules, it was rewriting them, sparking a firestorm of speculation that ranged from mundane cosmic dust to the electrifying possibility of alien technology. The mystery deepened when scientists combed through old photographic plates and realized this star's strangeness wasn't new. Over the past century, its brightness had plummeted by as much as 15% overall, a slow, inexplicable fade that contradicted everything we know about stellar behavior. Stars this age, roughly 1 billion years, should burn steadily for eons, not dim erratically like a dying flashlight. The internet erupted with theories, the most tantalizing being the Dyson swarm hypothesis. The idea that an advanced civilization could be constructing vast solar collectors around the star, harvesting its energy and causing irregular shadows as the megastructures orbit. But before we book flights to meet our extraterrestrial neighbors, let's examine the more grounded explanations. One leading theory suggests swarms of comet fragments or planetary debris, perhaps the remnants of a cosmic collision, could be trailing dense dust clouds that intermittently block the star's light. Observations in 2018 revealed the dimming events were wavelength-dependent, meaning shorter wavelengths of light, like blue, were blocked more than longer ones, like red. This fingerprint matches dust's behavior, ruling out solid megastructures which would block all light equally. Still, questions linger. How could natural debris create dips so dramatic and irregular? And why hasn't the dust dissipated over time? Another possibility involves intrinsic stellar variability. Some proposed Tabby's star might be recovering from a cataclysmic planet engulfment, a scenario where it devoured a nearby world, stirring up its outer layers and causing temporary dimming. Others speculate it could have a massive, uneven ring system or a family of Trojan asteroids trailing in its orbit. Then there's the stellar heartbeat theory, where the star itself pulsates in chaotic, unseen ways, though no known stellar model fully accounts for its extreme behavior. What makes Tabby's star truly revolutionary isn't just the mystery, it's how it's transformed citizen science. The discovery relied on data from NASA's Kepler mission, but follow-up observations were crowdsourced through projects like Planet Hunters, where amateur astronomers analyzed light curves from their home computers. When the star dimmed again in 2017, telescopes worldwide, from backyard setups to the Keck Observatory, swung into action, capturing real-time data in an unprecedented coordinated effort. This collaborative spirit underscores a profound truth. Sometimes the universe's greatest puzzles are too big for professionals alone. For now, Tabby's star remains an enigma, its secrets guarded by distance and the limitations of our technology. Whether the answer is cosmic dust, planetary wreckage, or something far stranger, this star has already reshaped how we search for anomalies in the universe. It's a reminder that the cosmos still holds surprises, and that the line between science and science fiction can sometimes blur in the most unexpected ways. From hypergiants dwarfing our solar system to zombie stars devouring their neighbors, we've witnessed the universe's most extreme stellar phenomena. These celestial titans defy expectations at every turn, whether it's UY Scuti's incomprehensible scale, Betelgeuse's explosive instability, or the raw power of magnetars strong enough to distort atoms from light years away. Each of these cosmic marvels rewrites the rulebook, proving that nature's creativity far surpasses our wildest theories. These stars do more than dazzle, they sculpt the cosmos. The iron in your blood, the calcium in your bones, even the oxygen you breathe were forged in stellar furnaces like these. When massive stars detonate as supernova or merge in violent collisions, they become cosmic alchemists, transforming simple elements into gold, uranium, and the building blocks of life itself. Their radiation carves nurseries for new stars, their gravity bends space-time, and their death seed galaxies with possibilities. They're not just points of light, they're the architects of existence. Yet for all we've uncovered, the greatest lesson might be humility. For every mystery we've solved, like deciphering Tabby's star's dust clouds or mapping Eta Carinae's hourglass nebula, dozens of puzzles remain. Why do some hypergiants pulse erratically while others fade quietly? What triggers the bizarre eruptions of luminous blue variables, and what strange stellar hybrids have we yet to discover? These unanswered questions remind us that the universe always keeps a few cards hidden. Now we turn to you. Which of these celestial powerhouses left you awestruck? Was it the haunting beauty of Mu Cephei's garnet glow, or the raw terror of a magnetar's magnetic field? Drop your favorite in the comments and share what fascinates you most about these stellar extremes. For those hungry to dive deeper into cosmic mysteries, hit subscribe and ring the bell. We're just scratching the surface of the universe's wonders. The night sky isn't just a ceiling of stars, it's an ever-evolving storybook, and you've got a front row seat to the next chapter. Keep looking up, who knows what impossible star we'll discover